So the first video from chapter 24 is an introduction to fields and to electric fields in particular. Okay, so first off, a little bit of motivation as to why we define this thing called the electric field to begin with. So last chapter we learned about Coulomb's law, and with Coulomb's law we could find what the force is between any two charges, or between some number of charges, right? It's just a lot of vector addition. So, in principle at least, we can use Coulomb's law to find the net force on some charge in the presence of any other number of charges. So, and this is what the equation looked like. So we've got our net force, so it's just the vector sum of the forces from each of these individual charges. So, one other thing to note though, so Coulomb's law always has two charges, right? So we have the charge we're interested in, the Q subject, so that's the one we're trying to calculate the force on, and then we've got all the other charges that are actually exerting the force on this thing, so those are the Q sub i's. So Coulomb's law always has two charges. So it would be useful to have something that describes the electric properties of a single charge or a charge distribution. So, and another note is that Coulomb's law quickly gets pretty complicated, so this is one of these things in physics that it's easy in principle, but can be difficult in practice, right? Because if you've got 100 other charges, then this is some big ugly vector sum that's going to quickly get pretty complicated. Okay, so that's why we introduced this thing called a field. So in general, before we talk about the electric field, just mathematically, so a field you could think of as similar to a function. So remember, imagine some function, so like f of x, right? So you plug in a number and it spits out a number, so that's a function. A field is similar, but a field has a value at every point in space. So you have things like a scalar field. So for a scalar field, for every point in space, you have some scalar value. So you could imagine the temperature in a room, say. So at every particular point in the room, you could define a scalar value, the temperature. And the temperature could be different at different points in the room. So that would be a scalar field. You could also have vector fields. So a good example is something like a fluid velocity. So imagine you have a river or a stream that's flowing, and at each point in the river or the stream, you could define the velocity of the fluid. So velocity is a vector, it has a direction, so that would be a vector field. Now in physics, we use these fields quite a bit, and the field has a source and a subject. So the source is where the field comes from, and the subject is the charge in our case that we're going to place in that field and that it's going to feel a force. And the important thing to remember is that the field only depends on the source and never on the subject. So with that, we can now define the electric field. So for the electric field, at every point in space, we're going to define a magnitude and a direction. And the magnitude and the direction, what it's going to be, it's the magnitude and the direction of the force per unit charge on some little imaginary test charge, Q test, we place at that point. So the electric field, we're going to use a capital E, it's a vector. It's the force that this hypothetical test charge would feel divided by the value of the test charge. So we're dividing out our subject, so that's why the electric field doesn't depend on the subject. So, and the nice thing about this, so once we know the electric field, the field can then be used to calculate the force on any subject charge, so now Q subject, placed at the point where the field is defined. So if we want to know what the force is due to this electric field, we just multiply Q subject, so that's the charge of our particular charge that we're going to place at that point, times the value of the electric field at that point. And of course the units, well, forces we measure in newtons, charges we measure in coulombs if we're in SI units. So the SI unit for the electric field is the Newton per Coulomb.